Hello everyone. Today let's take a look at a problem in Femap and try to model a single degree of freedom free undamped motion. Alright, let's get started. Here's a little reminder of all the values and concepts that belong to the simple harmonic motion. For us this will be undamped, and we're gonna try to model it and see how does this look in Femap. Alright. For some of you that watched our other video about free undamped motion with only initial velocity, the beginning part of this video will be exactly the same, all the way up to where we have to set up our initial conditions. From there on will be new, okay? But for those of you who didn't watch the other video, don't worry, everything will start from scratch in this video and show all the steps. Alright, let's get started by creating the nodes. Go to Model, Node, locate in work plane. Okay, so we're gonna put the first one at 0, 0 at the origin. The next one, put it at 1, 0. Okay, there you go. Those are our 2 points. Let's Control Q and in Mesh Node so we can visualize where they are and see their IDs 1 and 2. There you go. Next, we're gonna go to Model and set up our property. Here, we're gonna click Element Property Type, and we're gonna choose the Spring Damper option right here. Click OK. This is also called Type C-Bush. Okay. For the stiffness, we're gonna go ahead and enter 100. Right now, we're not gonna enter any damping, and that should do it. Click OK. That's the only thing we need to enter, so cancel it out. Now we're gonna go ahead and create our element right here. Make sure you go to the property and pick the spring damper property that we just set up. And between node 1 and 2, you can either select them or just simply enter it, because for us it's just 1 and 2. Leave everything as is for now, and okay, there you have it. We set it up. We have our spring damper set up. Next, we're gonna set up our boundary conditions. So we're gonna go to Model, Constraint, and Nodal. Right here, we're gonna BC for boundary conditions, and on the left hand side, we're gonna put a pin. Let's see, left side. We're gonna put a pin on the left hand side. That means this and this is zeroed out. Click OK. On the right hand side, we're gonna put okay, and we're gonna put we're gonna allow X transition in X, but not in Y, and Z translation in X, so our motion can happen back and forth, the simple harmonic motion in the X direction. See, because our spring is parallel with the X-axis, so that one we leave, the other two zero out. Okay, cancel it out. Now we're gonna add a point mass at this end of our spring, just like we see here in our sketch, the spring, and on this end it's gonna have a point mass. Okay, go to Model, Property. Here, Element Property, we're gonna set up an other element mass. There you go. This will be a zero-dimensional type finite element since it's just a point mass. Add the mass over here, add a weight, let's say 1 kilogram. Click OK. That's it. We don't need to add anything else. Now we're gonna go back to Model, create our element, which will relate the point mass to node number 2. So here it is. Go to Property, Mass Property, and assign it to node number 2. This one, right? Click OK and cancel. Now we're ready to set up our initial conditions. So I want to start the simulation from a point where the displacement is still 0, but we have an initial perturbation. Let me see. So I wrote it here. Initial displacement is at 0, but we will have an initial velocity 0.1 meters per second. So let's put this into Femap. So there's no such thing as initial velocity or anything specifically said over here, so you need to remember that it is under load. Okay, load nodal. Let's put IC, initial condition. Okay, we're gonna put it on node 2. Click OK, and then when this window comes up, we are able to see it in this list right here. You can find velocity, initial velocity. Okay, so remember it, it's under loads. Let's call it IC velocity value right here. We're gonna in the X direction, so put a 0.1, and that should do it. Click OK, cancel it out, and we don't need to tell Femap that we want it to start at initial displacement 0. If we don't say anything, it will automatically assume it is starting at 0. But here for our case we do have an initial displacement, so we need to enter that. And just like we had the initial velocity, we have to go to model, and again we have to go to loads and nodal. Click number 2 because that's where we're gonna apply it. Okay, and again we come to this window, same as the loads, right? So we're gonna put here initial displacement, and instead of velocity we pick displacement, and our initial displacement, let's see, 0.00, what did we say in the problem? 5. Yeah, there you go, 0.05 in the X direction. Alright, and click OK, and now we can see that we have, this is the symbol, cancel, this is the symbol for initial velocity, this is for initial displacement. Okay, we set everything up and we are ready to start our analysis. Go to model and analysis. It's not going to be a static problem, okay, with dynamic stuff. So let's call it dynamic 1, and see over here, this is why I said it, analysis type, not static. We're gonna go down to 3, transient dynamic time history. Okay, click OK. Now before we start analyze, we need to go under options and dynamics. Open it, see we have not defined, so click on it, open it, and here we need to define our intervals, the time. Okay, number of steps, how many time steps we want to run. Let's say I want 100 of them. The time per step, this is when you do hand calculations, this is your delta t, so 0.01. and output interval, when we're gonna be graphing it, we want to see a nice smooth curve, right? So we want the software to output the result every single calculation. You can put if you're doing some big calculations and you don't want to do too many data points to save time and space, you can put maybe, I don't know, 2 here or 10 or whatever works for your simulation. For us, this is small simulation, 1 will be just fine. Click OK. Now one more thing that we need to tell the software is down here under master. Open it up and go to boundary conditions. Open that up, and we need to specify, oh, I closed it. We need to specify our constraints. We set them up and we call them BC. There you go, it's already selected. If you look over here in the model tree, remember the name that we gave was BC. The loads, well, this is a free vibration, right? That means we do not have a forcing function, so none. We need to make sure we select none, but we do have initial conditions, and when we set it up, remember we called it IC, so make sure you select here IC. Okay, software needs to know this, and then click OK. Now we are ready to run the analysis, but before we click the button, let's take a look at the preview input. These are the cards,
the Femap cards. We'll have videos on these if you want to understand these further, but just a quick analysis. We can look at this initial condition line, and over here we can see our initial velocity was set at 0.1 and initial displacement is 0.05. Okay, and there's other information if you know what you're looking at that you can verify and make sure that they're correct. Done. You don't have to click on that if you don't want to. Just go ahead and click Analyze. Alright, let's wait for our solver to do its thing. There you go, and complete. Very good. No errors. Awesome.
Now that we have our results, we can go up here, right here, charting, open it up, and we can set up our chart right here. New data series, and here we can call it, I don't know, chart 1, or call it the name that you would like. Velocity versus time, displacement versus time. We're gonna model displacement versus time, so you can put u vs time. Okay, over here, let's see, here we're gonna pick vector versus set, output set value, and here we're gonna pick T1 translation, because our motion is in the X direction, T1 is X direction, and location where we have our result on node 2, right? Remember, over here, node 2, and click OK.
There you go, we can cancel this out. Done. And here it is, our simple harmonic motion with initial velocity and initial displacement. And if we look right here, come on, zoom in, we can see that we did not start at 0, right? Our displacement at time 0 is not 0, it is 0.05, and the slope of this line would be the initial velocity, which we marked as 0.1, right? So there you go. That is our graph for our simple harmonic motion. Alright, thank you for watching. Make sure you like and subscribe and tune in for the next one.